Hello and welcome to this session where we are developing the conservation equations. So up to this point in this part of the course, we've been developing the material balance, and we derived it for various situations in various geometries, sometimes in different types of coordinate systems. Sometimes we had spheres, sometimes cylindricals, sometimes rectangular or Cartesian coordinates. And in a way, we began to despair of this possibility that there were an endless variety of these problems. And each time we had to go through this painful process of developing these rigorous balances and defining each step. And in this session, we are going to generalize all of that. So we are going to show that all the equations we derived so far are actually just specific cases of a general understanding. And once we know how to use this general formulation, we can actually generate all the models and all the balances that we've described so far. And in fact, we are going to go beyond material balances. So although we developed that for the material balance case, we will show by analogy that this has applied in many branches of engineering. And in fact, then in this session, we are going to show that we can derive the equations that govern most of engineering. And in fact, what we will do, the approach we will take to show this, is right from the fundamental theorem of calculus. Right? In a way, this is your entry point to understanding anything about a fluid, and we will not miss a step here. So we won't make any jump, we won't make any assumption, we won't bring in any additional knowledge or any other kind of balance or anything else. Only from the fundamental theorem of calculus, we are going to generalize all our understanding and produce this equation that we promise describes most of engineering. Right, so with that kind of very bombastic claim, let's go straight into it. So the fundamental theorem of calculus, of course we know it's this, but we want to spend a few minutes just understanding better exactly what this equation is saying to us. And that's because we are going to build on this, so there will be many other concepts that draw from a strong understanding of what this statement really tells us. So this statement is telling us that there exists some function, and the difference between the values of the function at two locations, right? So the y2 minus y1, that's at x2 and x1. The difference there may be estimated by adding up the differences across all the values in the space x1 and x2. So it's saying there does exist a difference between the values of the function, but that can also be estimated by adding up the gradients, integrating across the gradients across the space. And a way to view that is if we select any point in the range between x1 and x2, if we choose a point, then at that point there does exist a gradient of that function. So if we look here, we've sketched out a couple of gradients. So at that point, if we integrate along that gradient, we will in effect be calculating a delta y. So for example, here, if you integrate a short distance forward, that will give us a small change in y, and that will lead us to the next point. And so if we keep doing that, in other words, if we add up all the small differences in y, then overall we will get the net change y2 minus y1. So that's a way to read this equation. And now we consider the divergence theorem. So the divergence theorem says that if we have a vector field f, and that's located in some region V with a boundary A. So imagine some three-dimensional blob, if you will, and that blob has, well, it's represented by this volume V, and it has a surface A. And we are saying here that if we integrate this vector field all along the surface, right, so this vector field exists throughout the volume of this blob. So the vector f has a value inside of the blob and on the surface, and but if we only integrate f on the surface of this blob, then we will get the same result if we add up all the changes on the inside of the blob. So instead of integrating only on the surface, if we integrate through the whole volume of the blob, and if we take all the values of f inside that blob, and if we take the divergence of f inside the blob, then adding up all the interior changes, that gives us the same as the changes that we can observe, or not the changes, the integral of f on the surface. And so you should be able to see the analogy between these two cases. This integral of f over the area is in effect the outer points here, right? The area, which is the outer surface of the volume, right, is shown by these points x1 and x2. So the difference in the function at these exterior points is analogous to this integral over the area. And then adding up the gradients through the volume is the same as integrating over the specific path for the gradients inside there. So there is an analogy between what is effectively the one-dimensional version of this three-dimensional divergence theorem. But if this doesn't make complete sense, if you don't see this with complete clarity, we are going to develop this in more detail now. So we will actually prove this. So again, we are only starting from this. We are not going to require that we have to accept this as yet. So let's prove this at least in Cartesian coordinates first. And to do that, we will imagine our vector field f, and we are talking about f through some volume. But the volume now is a bit more specific, so for simplicity, we are going to assume Cartesian coordinates, and we are going to take just a rectangular volume. So taking our rectangular volume in the coordinates x, y, z, the Cartesian coordinate system, we are going to consider x values between a and b, and y values between c and d, and z values between e and f. So that's our volume. It's basically a box. And our vector field f exists and is defined for every single point in the space. So if you pick a point inside the box, there exists a vector pointing in some direction. You can also pick a vector on the surface here that's a vector pointing in some direction. So that's the situation, and we can ask then, what's the flux if we interpret f as a flux, right? So we've been using the notation capital NA, but let's say f was a flux, and we are interested in the mass flux through this space. So here's our subvolume, and let's just think about the change in the x direction first. So we've got a flux arriving in at this face here, and then we've got a flux leaving from that face there, right? So looking at flux just in this direction, of course we have flux in all three directions, but just in terms of flux in the x direction, we've got material arriving here and we've got material leaving there. So we can write that the flux or the flow through these faces is in effect the surface integral of the flux. So in other words, if we are talking about integrating over the area here, right now we are just adding up the area flows here and here, right? And if you look at your flux on surface A1, which is well, let's see which way we did it. Yeah, surface 1 is here and surface 2 is there. Now note that we are not talking about in minus out, right? We are looking more generally at just what's the total flux across the whole surface here. So we are just saying there exists a vector field and we are integrating it over each area and adding up all those contributions. So for area 1, we can see that the flux is in the opposite direction to the outward vector, remember each surface has to is represented by a unit normal outward vector and a certain scalar which tells you how big that area is. So the area here is considered directional. So in the vector sense, the area is directional. So the area is represented as a vector. So the outward vector here multiplied by the vector field there. Now we've defined the vector field f to be positive in this direction for increasing values of f. That means at this point the default is that the vector field f is pointing into the space. So the area A is pointing out of the space. So these vectors are in the opposite direction. So the dot product is going to give us a negative, and it will give us the value of f. So minus the value of f is going to be the product there. And in this case, the f, we've taken just the x component. So we are talking about transfer in the x direction here. So we are just taking the x component of our vector f. So that's fx, and then that will have the x location of a. So that's the flux in at position x equals a. And then that's for all values of y and z, where y goes from C to D and Z goes from E to F. So C to D and E to F in Y and Z. So that's the flux, that's the flux arriving in at this phase here. And then the flux leaving from here, you can see Fx, this now is at position B, and we are integrating for y in the same range, C to D, and Z goes from E to F. So again, we are taking the component of f in the x direction, and we note that the x value is b, and so we are just integrating this over the area. So that's the contribution from the x direction. And in this case, it's positive. Your outward vector from this area is in the same direction as as f itself. So the product is going to be a positive, and so this is a plus fx, and then the area here is this is this value. Well, it's between c and d and e and f. So those are the contributions from the areas. And then if we look at these two terms, we can see that we are integrating over the same y and z space. So we can combine this integration and rewrite this as the area integral of the difference of this function fx, right, the x component of f, and the difference is in a and b for the x value of fx. So that's what we have here. And now if we apply our fundamental theorem of calculus, we said that the difference in a function, right, the value of the function at one point minus the value of the function at another point will equal the integral of the derivative of the function across that space. So instead of writing this difference, f of x at b minus f of x at a, we can say this is the derivative of f of x. So it's ddx of fx, and then over the range a to b. So we can replace this part by this integral, and this comes straight from the fundamental theorem of calculus. So we can replace this and say that the f integrals over the area is simply equal to dfx dx integrated over all dimensions x, y, and z. Now, if you look at what this triple integral is giving us, this is of course an integral over the volume, right? We are integrating in all three dimensions across all possible values of those three dimensions. So this is basically a volume integral. So this is the integral over the volume of dfx dx. And so we are starting to see what looks very much like the divergence theorem already. And of course, you can perform the exact same operation for the other dimensions as well, for y and for z. And so you can show that the integral over surfaces A3 and A4. So if you look in the y direction, surface 3 is at the base here, and surface 4 is at the top here. So if you integrate over those two surfaces, so the molar flux coming in here minus the molar flux going out there, then again you get here that the flux in this direction is opposite to the area vector, which is pointing downwards. Here the flux is in the same direction as the area vector pointing up. So following the same process as we discussed before, we get now for those axes, we get this similar formulation. And now, of course, if we want the integral over the area of the whole box, then we have to add up the integrals over each of these areas. And so we add all these together, and you can see here that we are integrating over the same space, over the same volume. So we can recognize the sum of all these as the integral over the volume of each of these derivatives, right? And that basically proves it now, because the divergence of f, right, is defined. Divergence is simply defined. It's simply defined as an operator. So the divergence of f is the gradient in each direction. So if you differentiate the function fx with respect to x and fy with respect to y and so on, and add them all together, then that gives you the divergence of f. So we recognize this as the divergence of f in v, so the integral of the divergence of f in v, and that's equal to the integral of f over the area. So that's basically the divergence theorem proved, at least in Cartesian coordinates. Here's just a short comment that you could also write the divergence. You could recognize that the divergence is something like the dot product of nabla operated on f. So this is not really a dot product because this is an operation. So nabla is it's a vector showing that gives us the gradient in each direction, and so you apply nabla onto some vector, and then the result of that is basically the divergence, right? So anyway, that's, if you are more familiar with this notation, then you can view the divergence as the dot of the Dell operator on the function as well. Anyway, you can also just stick to this form. So that's the divergence theorem, and let's apply that now to mass transfer. So we've talked about the divergence theorem in the abstract, and now we also talked about this abstract vector field f. Of course, we can instead think about a mass flux. So if in this original picture here, if these were all fluxes, and in fact when we talked about it, we did talk about flow through faces and of fluxes already, so we've already done this. But anyway, let's do it, I guess, for practice in this kind of abstract development. So if we consider the mass flux, right, as a convection flux, so your flux is velocity multiplied by concentration. So of course we know flux is a vector and concentration is a scalar. It's not directional. So yes, it varies across space, but the concentration is not exerting itself in any specific direction. So that's just a value, it's a scalar, and so because the velocity is a vector, then this product is a vector. So our flux is a vector, and so our flux, we are basically replacing the f that we introduced earlier by this flux. So if we go and apply the divergence theorem, well, actually I see here I haven't as yet applied divergence theorem. So first, let's just talk about the rate of change of the moles in some volume. So we've got some space. It doesn't matter what the shape of the space is, but there exists some volume, and if we integrate the concentration over that volume, then that will give us the number of moles in that volume. And we are interested in the rate of change of the number of moles in that volume. Now, if the volume is more specific, if the volume was this rectangular volume that we showed here, then the integration through the volume can also be written in terms of integrations in each direction, x, y, and z. So we can expand on this integral in volume as integrations in each dimension. And so acknowledging that the concentration is generally speaking varying in 3 dimensions, we can simply integrate over all 3 dimensions, and that will give us the total rate of change of moles there, and then that's the same as the left-hand side. So this whole expression is nothing but an expansion on the volume. And if we perform this differentiation, right, let's just perform this differentiation on the right-hand side, so ddt of these integrals, and of course if you differentiate that then if these are fixed end points, right, if you are familiar with the Leibniz rule for differentiation, you'll recognize that if these are fixed endpoints, and these are fixed endpoints for this rectangular geometry, they are not changing in time or anything like that, then we can simply rewrite this as the integral of the derivatives. So the derivatives shown here. Now, if we think about this function, the concentration is varying in all 3 directions. And also something that we didn't write in, which we should have and could have, but we could have also written that concentration may be a function in time as well. So the concentration field is changing in the 3 directions, but it's also changing over time. So when we do this differentiation in time, yes, we will have a derivative in time here. So it's it is possible to have one function like that emerging. And then if we differentiate also that the concentration may be changing with time due to flow in a particular direction. So in other words, if x is, if we are talking about this in the Lagrange sense, where an object might be moving in time, then we possibly have dx dt. So if we differentiate c, given that x might be a function in time as well, then the derivative here will be dc dx dx dt. So dc dx dx dt. And then similarly for the other dimensions, we can write dc dy dt plus dc dz dz dt. Right, so we can expand on this differentiation in time like so. And if we think about the meaning here, dx dt, dy dt, dz dt, so of course the rate of change of distance in time, that's nothing but a velocity. So we know that our fluid is possibly in motion, and so these are velocities. So dx dt, and so we recognize the vector u as we defined up here. We said that there's possibly a vector u, and now we are just acknowledging that that vector u has the 3 components ux, ui, uz. Okay, and yes, so that's the same idea here. And now we recognize then that this sum is actually the product. So if we replace these by ux, ui, uz, you can rewrite this as the product of dic dx, dic dy, dic dz, and u. Right, so all those gradients multiplied with the vector u is the same as this part of the balance. Right, right, that's there. Now, as I started to say earlier, we can also think about the Dell operator. So the Dell operator, and in fact normally we write it as Dell dot. So Dell dot f is basically, well, in fact here f is a scalar, so I'm not going to write the dot in. So del of f is, this is an operation, right? This is the Dell operator, so it operates on a function. So this operation is basically differentiating f with respect to all the variables in this Dell definition. So this is di f di x, di f di y, di f di z. So we understand this as basically a derivative of f in all possible dimensions of f. Note here that f is a scalar, but the derivative, the del of f, is actually a vector. So anyway, we can see here that we could rewrite this vector as del c, right? So just copying the same form over here, we can see that this is del c, right? Remember, this whole thing came from the derivative of c in these, so we can rewrite that as del c multiplied with u, right? So that is the form we have here, and if we compare that, right, in fact here this is actually taking a step backwards now and just reminding us that this is the same as this. We already showed that just now. Yeah, in fact I said all this earlier. We can recognize the del of a vector. We've been talking about del of a scalar here, but the del of a vector can also be written as the divergence of that same vector. So that's there. And in this case, the divergence gives us a scalar. So in this case, f is a vector, and so if you do del on a vector, you get out a scalar. Whereas if you do del on a scalar, you're getting out a vector. Anyway, we recognize then that the divergence of c dot u, where c is a scalar and u is a vector, that's the same as the del of cu. And so del is the operation in each dimension like this, and u is the vector in ux, ui, uz, all multiplied by the scalar c. And so if you do this multiplication, so it's this row multiplied with this column, then it's ddx of cux and ddy of cuy and so on. So we get this form like so. So that means in the equation that we've written here, we can replace all these terms by the divergence of c dot u. Right, so we go back to the original form that we had. Remember, it was ddt of c in v. And by the way, we sort of haven't been talking about this part of it as yet. We've been talking only about this part of the equation so far. And so we've shown that this part can be written as the divergence of c dot u. Okay, and now if you just compare left and right here, you can take the right-hand side across to the left-hand side. So basically this part minus all this equals 0, right? So we just move the right-hand side to the left-hand side and say the right-hand side is now 0. So just taking this across here. And we recognize again that we are integrating over the same volume. The volume is the same looking at x, y, z varying in these particular areas. So we can rewrite this as the integral of the volume, and then we keep what we had on the left-hand side here, and then we are subtracting out this function, so minus di c di t minus the divergence of c dot u, and all of that is integrated in v. So now we've taken that across, so what we're left with here is a 0 on the right-hand side, and we've got this form. Now, when we first proposed doing all of this, we never laid any restriction on the nature of v. Well, of course, we said it must be rectangular. We've simplified the way we are doing this, and we are working with a rectangular volume. But still, we didn't say, oh, x had to be that a and b on x. Let's go back to the picture. So we didn't say that there are only special values of a and b where we're going to draw this, or in any other dimension. We didn't say anything that a, b, c, d, e, or f, that they had to be in any special range. In other words, we could draw this box and write all these balances in any choice of those 6 values. And now we are saying here that that if we integrate over that volume where this box could sit anywhere, we are saying that if we go and integrate this function over this volume, we are always going to get 0. And think then about what kind of function can satisfy this requirement. And in fact, let's try and draw something like that. So let's imagine we have some space here, and we want to pick a choice here. So if we pick a choice here, and we say we are going to integrate over this space, then the integral of some function, we don't know, there's some function that we are talking about. So there's some function of interest, and we are saying now that we are going to integrate under that function in this region, or we could easily move it here, and if we integrate there, or if we move it here and we integrate just there, that we are always going to get 1. Now think about what this function must be. Sorry, I said it must always integrate to 1. That's not right. It must always integrate to 0. So the integral in any choice must give us a 0, the integral of our function. So this is the function y. So if we integrate the function y for any choice in x0 and x1, we are still going to get 0. It doesn't matter where we integrate. And so what possible value of y should this be? What kind of function gives us this? And you'll agree the only way to satisfy this for any choices in x is that y itself must be 0. So the function itself must be sitting on 0 if we are able to claim that the integral is always going to be 0. So if that's the case, if our volume is chosen over any range, and we can see in our development so far, we never specified anything about any kind of restriction. We never said any function depended on any specific values in x and y. So that means this always holds true, and that means the only possibility is that this function on the inside must always be equal to 0. So that's what we write here. We can say this kernel of integration must be 0 always. Now, if we further think about the meaning of this function, this term dc dt, that only arises if we have some explicit function of concentration in time. So if we have concentration as a function, and if there's a part of that which has an explicit dependence on time, then this term would be non-zero. So we understand this as a kind of forcing term. So it's a kind of generation term. So we will replace this dc dt as g of t, understanding it as a kind of generation. So we can say then that dc dt equals the divergence of c dot u plus the generation rate. So this is now our equation. And you see, all this arose directly from just a statement of that there is a flux across some arbitrary volume. Okay. Now let's think about applying this to a subvolume dV. So if we are looking at a subvolume and integrating this equation over the subvolume, then each term, of course, has to be integrated. And if your volume is small enough, so maybe let's just specify that we are now talking about choosing some tiny volume, some tiny space in our original overall volume. So we are now looking at just some tiny volume in some overall volume. Then we know this applies inside that subvolume as well. And so now if we integrate over this tiny subvolume, then we can say that if it's small enough, then these fields, right, in concentration and generation, those will be approximately constant over that volume. And in fact, to do it in the terms that we are more familiar with, let's work in terms of delta x, delta y, delta z, and of course then the product of all that is delta v. So the reason we do it this way is because we know we can take the limits for these things going to 0, and we can get a better expression there. So anyway, we can say we can approximate this integral, by simply multiplying the kernel by the volume itself. So delta v times dc dt is an approximation to this to this integral, and then here we are retaining this function as it is, and then the integral on the generation, if we take this to be approximately constant over the subvolume, then we can rewrite this as g delta x, delta y, delta z. Okay, and now if we divide through by delta x, delta y, delta z, clearly that can cancel here, and then we'll get 1 over delta x, delta y, delta z. And then in here, instead of using the integral over the volume of the divergence, we can use the integral over the area of the function itself. So this is an application of the divergence theorem. So we are just using the divergence theorem to replace the integral over the volume by the integral over the area, and we've then gone and cancelled out delta x, delta y, delta z. So we recognize this is a valid expression. Now let's think about what this equation means if we look in just one direction. So instead of thinking of u in all 3 dimensions, let's see what this means if we look at just one dimension, x. So dc dt equals the same stuff, and then now we are saying, and in fact another way to say it is, let's let u vary only in the direction x. So let's say the fluid is only flowing in the x direction, or we are only considering the fluid flow that's moving in the x direction. So we are ignoring other components of flow for now. So if we do that, then we can rewrite this as so c times u is going to be c times ux, and that's at that specific position, x, y, z. And then now the area changes over x only. So now it's c times ux, and now this is at position x plus delta x. And of course, this is all the integral over the area. And so the area now, the area normal to the flow, so the flow direction is x, so the area normal to that is delta y, delta z. And then if you look at this, your delta y, delta z can cancel with delta y, delta z here, leaving you with 1 over x, and here it's a function at x plus delta x, and the same function at x only. So you can easily see the derivative here emerging when you let the limit delta x go to 0. So clearly we are going to get dc dt equals ddx of this thing, right? And then of course we know that the flux, that this is the flux, so this is in effect NA, and we know NA equals the bulk flux plus the diffusion flux, and so we can replace this. We can say ddx of the overall flux will be ddx of the stuff on the right hand side here, so the ddx of this part and then ddx of this. If dE is a constant in x, then this is d2c dx squared, and then we've got left over g of t. Right, so that's if we only have velocity in the x direction, more generally, we have velocity in all directions, and so we will have terms for y and for z as well. Right, so that's the equation that we can generally write here. And then again, we can use the Dell operator to write this more compactly. So remember, Dell takes care of gradients in all three dimensions. And so we can write this as the del of UC. So you can see here ddx, ddy, and ddz. Let's see, is there an error here? Yeah, this should be a z, not an x, right? So that's a ddz. So that's nothing but the del operator. So we can say del of uc. And then you've got the second derivatives here, which you can think of as two applications of the del operator. So it's the del of the del gives us the second derivative. So we can say del of c, so that's the second derivative, and then of course the effective diffusivity is a constant there. Okay, so that's the equation, and we can of course then rewrite this as dc dt equals u del c minus de del squared c plus gt. So this equation is nice and general now, and what's nice is it's written in terms of this del operator. And the great advantage of recognizing a del operator is that it becomes agnostic to our coordinate system, because we can define del for any coordinate system. So far we've been talking about the del operator for the Cartesian coordinates in x, y, and z, but we could also determine the del operator for cylindrical coordinates. So remember when we looked at flow in a pipeline, then we had r and z. We hadn't really talked about theta because there were no changes with respect to angle in those problems. But generally speaking, we could include that as a third dimension. So in the case of the cylindrical coordinates, del of f looks like this, and then del squared of f looks like that. And so for cylindrical coordinates, the equation changes, so the expression for del changes, but the equation here stays the same. So it doesn't matter what coordinate system we have, the equation stays the same. It's just that if we look at particular dimensions, then this del definition may change. But we've got the same framework that applies now. And by the way, for spherical coordinates, these are the three dimensions. You have an r, radial position, and you have two angles. So in spherical coordinates, those are the appropriate variables, and the del operator looks like that, and del squared looks like that. So you see, for these three coordinate systems, we have again the same equation. And in fact, other coordinate systems could be imagined. You could imagine maybe some kind of triangular coordinate system, or something based on hexagons, whatever you like. So whatever coordinate system you want to work in, whatever system is the most convenient for your process, you go ahead and work out what the del of that coordinate system is and the del squared of that coordinate system, and you will find that you can apply the same material balance. So you see, in contrast to all the work we've been doing so far, where we always had to go and write little balances in every possible dimension, and we felt, I've done all this in this dimension. The same two processes are involved, the same diffusion and convection is going on, and yet I'm having to do all this work just because now I have a cylinder instead of a instead of some kind of rectangular or some kind of spherical space. I now have so now it doesn't matter what the space is like. It doesn't matter what coordinate system we have. We have the same equation, and we just have to look up the right del expression for that coordinate system. So that's one major generalization for us. We no longer have to concern ourselves with the nature of the geometry. The other thing is that now we've derived this expression, and it's general. We can say that the convection term always looks like this, the diffusion term always looks like this, and then it's just a matter of looking for our system. Do we have convection? If we don't have convection, then U is simply 0 and we ignore this term. If we don't, if diffusion is much lower than convection, then we don't have that term. So it's a question first of what's the relative rates among these, which terms are retained, and then after that we can ask what's our coordinate system and just apply the appropriate definitions for del and del squared, and then we'll get the right equation. Now, all that is a really nice generalization of the work we've done so far, but we should recognize that in the other balances that we've been seeing in the earlier parts of the course, a very similar expression has resulted. So if you think back to the energy balance that you did, right, you had a similar accumulation term, you had slightly different factors out in front. So your heat capacity related content was here. And then you also had convection here. So energy was simply carried into and out of the system due to bulk movement. And that's the same as mass carried into and out of by convection. So it's the exact same concept here. And then in terms of your conduction, right, so you had a conductivity and a conduction flux. So you had conduction through your material. So conduction is exactly the same concept as diffusion. This is just in the energy sense or the thermal sense. So you've got an analogous expression here. And then we sometimes talk about generation of heat, which really just means we are translating energy from one form to another. So you can see the exact same type of equation here as well. And then if you think about your momentum balance, in your momentum balance, you also had a kind of density times velocity term here, and that was multiplied with the del of your velocity. So you had a gradient in velocity multiplied by the velocity itself. And then you had viscosity here. So you had viscous drag, and so due to the differences among the neighbors, due to the differences in velocity across the neighbors, you had viscous drag, so you had some inertial pull on your fluid. And again, that's the same concept as conduction and diffusion. So you have basically diffusion across your neighbors, and so this is in a sense diffusion of momentum. So that's your viscosity expression. And there also perhaps you had introduced a pump or some other source of momentum. So you expressed that perhaps as a generation here. So even across the different types of balances that you've seen, we are starting to see a pattern here as well. And yeah, there's just an extra note here on momentum, that there are some specific forms of the generation. So sometimes because of the differences in height and sometimes differences in pressure, those are more specific forms of generation of momentum. And those are what we have in chemical engineering. And then yeah, I sound like a salesman now, but just here's one for free. So here's in electrostatics. So in the electrical engineering world, they also have the same form of equation. So I guess E is your potential difference, and then the gradient in that potential multiplied with the current. So I is the current. Remember, this is nothing but the flow rate of electrons. So it's analogous to velocity, right? That's the flow of electrons. So that's a rate of flow, and then that's a gradient in potential. So this is a convection in the electrostatic sense. And then you also have diffusion in the electrical sense. To be honest, I actually don't know enough about this field to say a lot about the meaning of these parts, but that is in effect the diffusion of the electrostatic field. And then yeah, if there's a source of energy that influences the electrostatic field, then you have that as well. So look up the Poisson equation and you'll see that you have also an analogous version of the equation. So if you look among all these equations, you can see that there's a convective part, so there's a velocity and a gradient in some function. So let phi be this generalized function. So whether it's concentration or temperature or velocity or potential field. So there's that phi. So there's a gradient in phi multiplied with the velocity, and then there's a second gradient in phi multiplied by some dispersive or diffusive or conductive factor. And then there's possibly some kind of forcing function. There's something that's contributing to that field from the external environment. So you see, all of engineering, in a way, is represented here in this one equation, right? So it's generalized geometry, it's generalized the nature of the balance that we are undertaking, and it's our kind of most general understanding. So this is one of the great achievements of the human mind. I don't mean mind. I mean the Navier-Stokes equations and the conservation equations and all that. And this now allows us to abstract our knowledge and tie it to one framework, which unifies all our understanding. And in addition to unifying our understanding, we find that it also leads then to a more efficient way to seek solutions to our problems. So what we'll do in some upcoming exercises is similar to what we started with earlier. So earlier we had described some physical situation, and we had derived the equations from scratch and built them up piece by piece. So what we'll do in the coming exercises is start from this equation and then look at the situation that's being described, decide which terms are retained, decide then what kind of coordinate system to apply, and thereby find specific forms of this general equation. And so that is a much more efficient way of developing our models, as we'll see. Okay, there are some useful problems to work through here, and these are in effect your tutorial 3, which comes up in the coming week.